Hi, and welcome to this section of the Probability and Statistics Tutor. And in this section, we're going to continue learning about probability distributions, and we're going to tackle the Poisson distribution, okay? So what you'll find out when you crack open your statistics book is that once you start learning about probability distributions, you'll find that there's a whole bunch of specific types of distributions that apply to certain kinds of problems, okay? We learned about the binomial. The binomial was applicable to a very specific type of problem. You know, you have n trials, so many successes within those trials, only two choices coming out of it. It had to really line up exactly, but if it did, we could use binomial, and it wasn't too bad once we knew that, okay? The Poisson distribution is just another kind of probability distribution that applies to a different type of problem. It's the same point though. You're going to have a different function that's called the Poisson distribution function that you'll write down to solve these problems, and you'll really do it the same way. Once you know how to write them down, then calculating the answer given the information in the problem really isn't that big of a deal. Now the other thing with the Poisson distribution is that it can sometimes be used to approximate a binomial distribution, okay? The good news is that the Poisson distribution, once we write the function down in a minute, I'll show you, it's really not as complicated to write down or to calculate as a binomial distribution. So it's actually kind of a simpler probability distribution to begin with, which is nice, okay? And under certain conditions, you can actually use the Poisson distribution to approximate the binomial distribution and get an answer that's pretty close to the actual binomial distribution, which is the correct answer, okay? This is useful if you're, not so much nowadays, but because we have such fast computers, but maybe 15 years ago when the computers weren't quite so fast, calculating a binomial distribution, you know, 10,000 times in a row, let's say you're doing a study or something, could be very computationally time-consuming. It could take a long time to do. But if your problem really fit in a certain mold, you could use a Poisson distribution to approximate it, which is much simpler to calculate, gives an answer that's pretty close but not exact, and it might be perfectly acceptable for what you're trying to do. So most of the statistics books will tell you that you can approximate the binomial distribution with a Poisson distribution, and we'll do a couple of problems to show you what that's all about, so it doesn't scare and confuse you. It's really not a big deal at all. The easiest thing to do to actually dive into Poisson is just to go ahead and write down what it is, write down the function, and then we're going to do some examples that you're going to find it's not going to be a big deal, okay? So the big deal to remember before you even write anything down is that the Poisson distribution really applies to occurrences of some event over a certain time interval, okay? And you'll see what I'm talking about when we get into the problems. Over some type of interval. You might have an average number of raindrops that fall into a bucket, right? And then over a certain period of time. And then I might ask you, well, how many buckets, what's the probability that 50 drops will fall into that bucket over a 1 minute period? Or what's the probability that 25 drops will fall into there over a 1 second period? You see, it's all about something happening over a certain period of time. Or even it could be over a certain surface area or something. The certain number of events happening in that time window, that is very useful for a Poisson distribution, and it's really useful everywhere. I mean, if you're trying to calculate the probability that a part might fail in your car or in your television or any kind of manufacturing, it might really be useful for you to know what the probability of two components failing over the next 50,000 hours might be, because maybe you're trying to design this TV or whatever to design to be last for 50,000 hours. So Poisson might come in handy there. So let's go ahead and write it down and see what it's all about. So the Poisson distribution, and I'm really going to write down a lot of what I just said just to make it clear. It applies to occurrences of some event over a specified time interval. Okay, that's exactly what I just said there. Now x, which is always going to be a random variable, so I'm going to put this down, random variable. Okay, x is the random variable, is going to be equal to the number of occurrences of the event in the interval. So I was just telling you that we might be interested to know what the probability of getting 2 parts fail within the next 10,000 hours or something is. Well, x is our random variable. That is the number of failures, let's say, in the specified time interval. So what you're going to do is you're going to have a function f of x. This function is going to give you the probability back of having that many failures, let's say, in a certain time interval that you predefine. So without talking about it anymore, let's just get on to it. The Poisson distribution is defined as f of x is equal to mu to the x, I'll tell you what mu is in a second, times e to the minus mu, all divided by x factorial. Okay, so this is the Poisson distribution function, okay? And some of the books, the mu's here that represent the mean value that we'll learn about as we work some of these problems, the mean value of some occurrence over some period of time. Sometimes they're listed in terms of, instead of mu, sometimes they're listed in terms of lambda. So when you see a book that has lambda to the x, e to the minus lambda then that's exactly what it is. It's just the average value, and we'll work some of that. Don't worry about that too much now. It's really easy to calculate that, okay? So big picture, this is a probability distribution function. It has some mean value of something occurring that you'll see in the problems, and then this probability distribution is going to be the probability that that a certain random variable has a certain number of occurrences in the specified time interval. So it could be the probability that 3 raindrops will fall into this bucket in a period of 1 minute, or it could be the probability that 10 raindrops will fall into this bucket in a period of 1 minute. So all of these problems, when you're doing the pure Poisson distribution problems, they're all going to involve some time interval or some sort of interval that you're going to look over, some number of occurrences happening in a time interval. So that's the real key for the Poisson distribution. If you have a time interval or something happening per unit time or per unit area or something like that, where you're looking for a number of occurrences to happen in a certain area or time or something like that, that's what you're really going to use the Poisson for. Now, the Poisson distribution actually has some pretty interesting things associated with it. The mean, we've already talked about it. Just like we already talked about the mean of the binomial distribution and how to calculate it, the mean we already know is mu. And that's actually going to give us, this is what I just told you right here, the mean is mu, and that's what's usually going to be given to you in the problem statement. And I'll show you how to pull that out. But interestingly enough, the standard deviation for the Poisson distribution is the square root of mu. And that's not something that should jump out at you as being obvious. That's just something that falls out of this particular distribution. If you go in and beat this thing into shape and start looking at how it behaves, you'll find that when you write something like this, the mean, when you write it like this, when you have a mean of mu, then if you look and you calculate the standard deviation, which, by the way, you know how to do. We've shown you how to calculate the standard deviation of probability distributions, but if you go off and do all that math, you'll find that the standard deviation of this particular function is just the square root of the mean, which is actually very, very easy. If you know what the mean is, you know what the standard deviation is, right? Okay, now we're going to work some problems in a minute, and some of them are going to involve, like I told you about, where you have a probability of a certain number of events occurring within a specified interval. That's exactly what the definition of Poisson is, and that's what it's really used for. But it turns out that you can actually also use the Poisson distribution as an approximation to the binomial distribution, right? So we know what the binomial distribution is from the last section, right? And we know what that is. We know how to calculate it. We know how to write it down. We know what it means. We know the types of problems we can use binomial for, okay? But we can also use the Poisson distribution to approximate that. And so the way you do that is, in order to, I'm just going to put it this way, you can approximate the binomial distribution with the Poisson distribution if 2 rules of thumb are met. Okay, and these are just rules of thumb. If you're given a binomial problem, you remember what you have to know for binomial distributions. You have a number of trials in trials, and you have a probability of success. And there's some other things in there, but those are the 2 main things. If you're working a binomial distribution problem and the number of trials is greater than 100, okay, and the number of trials times the probability of success is less than 10, then you can use the Poisson distribution as an approximation to the real answer, which is the binomial distribution, okay? And these two things will have to be met, okay? And if these two things are met, then you can use the Poisson distribution, just like we said above, with mu is equal to n times p. So what does all this mean? We're going to work some problems and make it all clear for you, but I'm just sort of giving you sort of the preamble here, okay? We learned about the binomial distribution. We know how to use it. We know how to calculate it. But the binomial distribution is actually a little bit more complicated than this, especially if you have very large n's and very large x's, because if you remember back to the binomial distribution, it had that combination thing in front, and that can be tedious to calculate, especially before computers, before very fast computers, okay? So this Poisson distribution is created and used for certain types of problems that we're going to work in a minute, just exactly what we were talking about up here. Intervals and the number of occurrences in a certain time interval, etc., okay? But it has a dual function. You can also use this function to approximate the binomial distribution function, which basically means that you can use the Poisson distribution to get an answer for a binomial problem. It won't be exactly right, but it'll be pretty close for, probably for what you're looking for, with a lot less computational effort. And we're really talking about problems where you'd want to do this in a computer, where you had 10,000 runs to run to test the parameters of your study or something. And if the binomial distribution is taking up too much computer time, you could probably use a Poisson distribution. But in order for the approximation to work, the number of trials in your binomial trials has to be greater than 100. It's a rule of thumb. And the number of trials times the probability of success p, the product of those two things should be less than 10. If both of these two things are correct, then go ahead and use the Poisson as an approximation, and it'll be pretty close. If these two things are not true, you could still use it, but the answer that you get from the Poisson approximation is not going to be very close to the real life answer. But if these two things are true, then the answer that you get is going to be pretty darn close. So if you decide to do this approximation, then all you do is set the average value mu equal to n times p, and then you use this mu, which, by the way, if you remember, is the average value of a binomial distribution. You use this average value to go up and plug that into the mu up here. So if you know n and p from a binomial distribution, you take the product, find the mean, and then you come up here and just put that into here, and then you have the Poisson distribution, which is actually pretty easy to calculate, okay? So I think we've gone over the basics of what the Poisson is for. We've also gone over the basic general idea of the fact that you can use it as an approximation to a binomial distribution, okay? But now we need to go ahead and apply it to some real problems so that you can get some experience with how to actually deal with it. So here's sort of a classic example of a Poisson distribution problem where you'd really want to use this type of distribution function to solve it. The problem says you're studying a cesium atom, which is just one of the atoms on the periodic table that happens to be radioactive, okay? You're studying the cesium atom over 365 days, very long time, and you start out, let's say you know that you start out with 1 million atoms, and after 365 days, those atoms decay because of radioactive decay. They decay into 977,287 atoms. Let's say you had some method to count the atoms. You started out with 1 million. Over 1 year, they decayed into something less than 1 million, 977,287 atoms remain, okay? Question 1 said, part A says, here, what is the mean number of atoms that decay per day? Okay, the mean number of atoms that decay per day, okay? And we're going to use that mean number because if you go back up here and look in your Poisson distribution, you need to know the mean. You need to know the mean value of whatever it is you're talking about per unit time. You see, this applies to occurrences of some event over a specified time interval. X is the random variable, is the number of occurrences of events in the interval, and the mean value of these events per unit time we'll talk about here, that's going to be mu. That's what you're going to use. So this is a number, and you're always going to have to know what mu is in order to actually use the Poisson distribution. And they're giving you the information to calculate mu because it says you start out with 1,000 atoms, and you decay into something less than 1,000 atoms. You know it happens over a year. So part A, I'm easing you into this. Part A is just, first of all, just calculate the mean number of atoms per day that have decayed. So let's do that, and then once we do that, we'll actually go into the Poisson part of it and go from there. So the mean number of atoms per day is going to be mu. That's my average value of decays per atom decays per day. It's the number of atoms for this problem that decay per day. And I'm kind of easing you into this. We're going to calculate this first. The next part of the problem, we'll talk about the Poisson thing and actually use this number. So mu is basically going to be, just in words, the number of atoms that decay in 365 days. That's the total number of atoms that decay divided by 365 days. That's going to give us a unit of number of atoms decayed per day, because it has the total number of atoms that decay divided by the number of days. So we're getting the number of atoms per day. Okay? Now what we know is we start out with 1 million atoms, and we know that we end up with 977,287 atoms. So we're going to subtract those. This is going to be the number of atoms that have decayed in the whole year. Okay? And we're going to divide that by 365. Okay? And so when you do that, when you take the 1 million, subtract the 977,287, divide by 365, you will find that 62.2 atoms per, that's the slash here, per day. Okay? That is the answer to part A. The average number of atoms that decay per day is 62.2 atoms per day, and that's just because we know how many atoms total decayed and we know the length of time. Now for every Poisson distribution problem like this, you're going to have to calculate mu. You're going to have to calculate the average number of events per whatever that time interval is in order to move forward and use it, and so you're going to have to basically do this every time. It's going to follow something real similar. The second part of the problem simply says, what is the probability that on any given day 50 atoms decay? Okay, 50 atoms decay. So this is what should clue you in that it's a Poisson distribution, because the problem says, what is the probability that on any given day, that's my time interval, any given day, okay? And I told you every Poisson problem is going to have a time interval associated with it, number of events that occur in that time interval, like the number of drops of water or raindrops that might go into this bucket in 1 minute. What's the probability of 5 of them falling in 1 minute? What's the probability of 10 of them falling in 1 minute? The time interval's fixed. That's what it says here. We know the average number of atoms that decay in a day is 62.2. We know that because that's given to us in our data. But we want to know, what's the probability that on any given day that I pick, only 50 of them decay? So we know that that's not equal to the mean number that actually decay per day. But we also know that on any given day, radiation decay is kind of a random thing. You may have more or less than 62.2 atoms. That's an average number. So what we want to know is, what's the probability that only 50 of them decay? We know that there's a time interval. That's 1 day. Okay? We're trying to find the number of occurrences of some event. That's the number of decays that occur in that 1 day. That's why it's a Poisson distribution problem. Notice that this doesn't read anything like a binomial distribution problem. We don't have n number of trials. We don't have certain number of successes within a trial. We don't know a probability of success and a probability of a failure, like a true-false type of questions on a test like we were doing before. This form of a problem is completely different than that. So you should, when you read them, realize that and not try to just use the binomial and get yourself in a trap. You should try to recognize what it's asking you and what type of distribution applies, okay? So because we're trying to find out the probability that 50 of these things will decay in 1 day, what we're going to do is we're going to use the Poisson distribution function, which is written as mu to the x times e to the negative mu over x factorial. Now notice that we just calculated the average number of atoms per day that decay. That's my mu. So this is going to be a number, and this is going to be a number, and the only thing left in this whole function is x, which is my random variable. That's the thing that I plug in to find out the probability of it happening. So what we really want to do is we want to use x is equal to 50. That would be 50 atoms decay, a probability of 50 of them decaying in my time interval, which is 1 day. The reason why the time interval is 1 day is because when I calculated the mean, it was atoms per day that I calculated. So the day, the single 1 day, is my sort of implied time interval here for this problem. Okay? So because I've already calculated the mean, the actual Poisson distribution function is 62.2 raised to the power of x times e to the minus 62.2, okay? And you divide it by x factorial. This is a function, just like a function from algebra 1, right? E to the minus 62.2, and put parentheses around that if that helps you. This is just a number. And by the way, if you're unfamiliar with negative exponents, this just produces a number just like anything else. You could slap it in your calculator and hit e, which is, by the way, 2.7. It's just a number, 2.7, raised to the negative 62.2. You're going to get a number. And that's going to be a number. And then so over here is going to be 62.2 raised to the power of x, and this is x factorial. So I could use this Poisson distribution to find the answer to a whole bunch of problems. I could ask myself, what's the probability of 50 atoms decaying per day? I could plug x is equal to 50. That's what we're going to do for this problem. I could calculate the probability that 0 atoms decay in that day by plugging in 0. I could calculate the probability that 100,000 atoms decay in that day by plugging in 100,000. And it's going to obviously be a low probability if I do that, because the mean is only 62 atoms per day. So obviously if I put 100,000 in here, I'm going to get a very low probability. Okay? And so you can do that for any number of problems. But in this particular problem, we want to know the probability of 50 atoms decaying per day. My random variable is the number of atoms that decay per day. Every different number I put in here is going to give me a different probability for that many atoms decaying in a day. So what it's going to be is 62.2 raised to the power of 50, because I'm plugging in x is equal to 50, e to the negative 62.2, and you're dividing the whole thing by 50 factorial. Okay? So when you actually do all of this, the top, 62.2 to the 50 times e to the negative 62.2, is going to be 4.75 times 10 to the 62. Very, very, very big number. This is basically 62 decimal points to the right, okay, divided by 50 factorial, which I'm not even going to attempt to write out because it's 50 times 49 times 48. Very, very big number. So the probability of 50 decaying in a day, when you actually do that, is 0.0155. That is the answer. So what we did is we had a problem where we were given the information to calculate the average number of decays per day. All the Poisson problems are really going to be like that, so you'll have to calculate mu. Once you know mu, that's all you need to identify what the probability distribution function is going to look like, which is this. After that, we were interested in the probability that 50 of these things decay in a day, so we plugged in 50, we get the answer. Now notice, the probability of 50 decaying in a day is pretty small. And that's because the average number of decays per day is significantly different than that, 62.2. So if the average number of atoms per day is 62.2, then obviously if you get far away from that average, the probability is going to go down that that's the number of atoms you're going to have on that day. And if you put other numbers in very far away from the mean, you're going to get lower and lower probabilities because well, that just sort of makes sense. If the mean is given to you by a certain number, then the farther away you get from it, the lower probability that that's what's going to happen on that particular day. Okay, the next problem says an island in the middle of the Pacific or something, reports that over a 20-year period, 196 tourists died, okay, on that island. So it's not maybe the best tourist destination, right? 20 years, 196 tourists died. First part, I'm going to do it exactly the same way to help you get your bearings. What is the mean number of people that died that year? And then, of course, we're going to, per year, I should say, per year. And then we're going to use that number to go ahead and find the Poisson distribution and calculate one of the probabilities here. So we're going to use the information to calculate the mean number of people that have died per year. So to find that, the mean number of people per year is going to be 196 people died divided by a 20-year period. So it's people per year, okay? And when you do that, 196 divided by 20, you'll find that 9.8 tourists per year died on that island. So that is what mu is, okay? So that's just the first part of the problem. The second part of the problem says, what is the probability that 0 people will die next year, okay? And then you could also calculate something different. What about 4 deaths per year? Okay, so we know what the average number of people per year dying is over a 20-year period. And now you can see it fits in the mold of the Poisson distribution because we're given that information. And now we're asked, In that same time interval, there's a time interval here that's a very big clue that it's Poisson, okay? What is the probability that 0 people die the next year, which is the same year, the next time interval of the same unit, the next year, what's the probability that 0 people die? What's the probability that 4 people die? Okay, so what we need to do is write down the Poisson function for this problem and then just plug it in. This is actually pretty easy to do compared to the binomial problems. So the Poisson distribution function, to refresh your memory, is equal to mu to the power of x times e to the minus mu over x factorial. Okay, because we've calculated mu, 9.8, it's 9.8 raised to the power of x times e to the negative 9.8 over x factorial. So same thing as before, e to the negative 9.8 is a number, okay? X is my only variable I have here, and that's my random variable. Every number I put in here is going to give me the probability that that many tourists die in the year, okay, given my historical data. And notice it looks nothing like a binomial problem. It doesn't have a number of trials. It doesn't have a probability of success or failure. This is a completely different mold of problem, and that's why it's a completely different probability distribution function, okay? To answer the first part, what is the probability that 0 people are going to die the next year? We just plug in x is equal to 0. So we get 9.8 to the power of 0, e to the minus 9.8 divided by 0 factorial, okay? Well, anything raised to the power of 0 is actually 1, you should remember from your algebra. And 0 factorial is also 1, so basically what you're going to have is e to the minus 9.8. So when you put that in your calculator and calculate what e to the negative 9.8 is, you would get 0.0000555. So a pretty low probability, and it makes sense that it's a low probability. If you have a 20-year history that these people are dying at a rate of almost 10 people per year, it's a pretty low odds, a pretty low chance that on the very next year nobody at all will die. Of course it could happen. That's what all probability is about. Things can still happen. It's just giving you a relative measure of how likely it could happen, okay? So let's go ahead and just work the last part of the problem. What's the probability that 4 people die? You plug in x is equal to 4, and you'll get 9.8 to the power of 4 times e to the negative 9.8 divided by 4 factorial. Okay? And when you put this in your calculator, 9.8 to the 4th times e, which is, by the way, 2.7 to the negative 9.8, multiply that together on the top, you get 0.511, and on the bottom, you'll still have your 4 factorial, which you could multiply out. So at the end of the day, the probability of 4 people dying is 0.0213, which is again also fairly low because, like I said, on average, almost 10 people are dying per year. So the probability of 4 people dying is going to be pretty much, significantly less than that. Doesn't mean that 4 people couldn't actually die next year. It's just the odds are low that's actually going to be what happens. Okay, so those are some problems where you're using the Poisson distribution in sort of the classic way. You have a time interval. You're trying to find the probability of a certain number of events happening in that time interval. Okay, so that once you know the mold of the problem, really doing those kinds of problems isn't a big deal. You calculate the mean number of events per time or per whatever, and then you write down the distribution function and you use it to calculate whatever you're trying to calculate. Now the second thing that you can use it for, we talked about, is you can use the Poisson distribution as an approximation to the binomial distribution. Okay, you know how to use the binomial distribution, that's fine, but I think you can see that this is actually in some ways a lot simpler than the binomial distribution, so maybe it's advantageous, and on your test it might actually tell you, use the Poisson function to approximate the binomial, so you need to know how to do this, okay? So let's go ahead and work it. The first problem is 5% of TVs are defective, okay? What is the probability that 2 of 100 TVs are defective? And also the problem specifically states use the Poisson approximation to the binomial. So just before we even do anything with Poisson distributions, reading this problem, we have, what we're trying to find is what's the probability of 2 of 100 TVs being defective, okay? So we have 100 trials, so we know n is equal to 100. We know we're trying to find that 2 and only 2 TVs are actually defective, so we have two events in 100 trials that we're trying to find. We know the probability of a TV being defective is 5%. So this is a straight up binomial distribution problem, okay? It doesn't look like a Poisson problem, it doesn't smell like a Poisson problem, and it's really not a Poisson problem, it's a binomial problem. So we could write everything down that we wanted to, and we could plug it into the binomial distribution and we would get the answer. But if certain things are true, we can actually use this simpler representation to get an answer that's pretty darn close, you know, and that's a little bit easier to calculate. So let's do that. First thing you always want to do is write things down. We know that n is equal to 100 because there's 100 trials, basically. There's 100 TVs, just like the section on the binomial distribution. X is the number of, quote, successes in trials, so there's 2 successes, meaning defective televisions. The probability of, quote, success, in this case defective television, is 5%, which is 0.05. Okay? And because of this, we know that Q is 1 minus P, if you remember back to your binomial. And if you do that, the probability of in this case, a non-defective television or a healthy, perfectly good television is 95%, which is 0.95. So right now, at this moment, we have everything on the board to solve this problem with a binomial distribution. We know n, we know x, we know p, we know q. We could write down the binomial distribution, and you know, we would get the answer. So just because we can do it, let's write that down. The binomial, the way you would write the binomial thing down here, it would be 100 in combination with 2, okay, times p, which is 0.05 to the power of 2, times q, 0.95 to the power of 98. Okay, this is my two defective televisions. These are my 98 healthy televisions, and these are the number of combinations I can arrange them 2 at a time out of 100. Okay, so keep this alive in the back of your head. We're going to come back to that. This is the binomial, which we've done extensively in the last couple of sections. So that should look fairly familiar. That's something we've done before. But let's ask ourselves, can we use the Poisson distribution to approximate the binomial distribution? There's 2 constraints. Is the number of trials greater than 100? Well, in this particular problem, the number of trials is exactly at 100. So, you know, this is a general rule of thumb. Let's go ahead and put a check mark there. We can probably use it. It's going to be right on the hairy edge of being a valid approximation, but it's definitely in the same ballpark. I mean, you know, 100 here, greater than 100. I mean, it's right there on the boundary, so we're going to go ahead and use it, okay? The second thing is n times p must be less than 10, okay? Is this true? Okay, what is n times p? N times p is 100 times the probability of success, 0.05, which equals 5. 5 is definitely less than 10, so both constraints, both conditions are validated, so we can use the Poisson distribution to approximate this binomial distribution here. So in order to do that, we always have to have, in order to use a Poisson, we have to have a mean, and back when I told you how to do this approximation, the mean that you use is n times p, which we just calculated, which is 5. Okay? So basically what you've done is you said, okay, this is a binomial problem. Can I use a Poisson approximation? Yes, these 2 things are true, so I can do it, but in order to use it, I'm going to use a mean value of 5, n times p, and those are the parameters from your binomial distribution, and so once we do that, we can do it. So the Poisson function, just to again refresh your memory, is mu to the power of x e to the minus mu over x factorial. Okay? Now we were told to use mu is equal to 5, so it'll be 5 to the power of x times e to the minus 5 divided by x factorial. At this moment, we have an approximation of 2 totally different functions. This is a Poisson function. Okay, so we'll write it down here, Poisson. This is a Poisson distribution function. It looks completely and totally different than the binomial thing, but what we're saying here is, because these 2 things are true, this is going to give answers pretty darn close to this up here. You know, within a certain error, but it's going to be pretty darn close. So if I wanted to find f of 2 or f of 3 or f of 4 or whatever it was, in fact, because I have 2 here, this is actually written for f of 2. If I wanted to put whatever number into this distribution function I wanted to, I could calculate the same equivalent number down here, and they should agree pretty closely. So because we're trying to find the probability of 2 defective televisions, we're going to use x is equal to 2 for this approximation. So it's going to be 5 squared times e to the minus 5 over 2 factorial. Okay? 5 squared is 25 times e to the minus 5. On the top, you're going to get 0.168. On the bottom is just 2 because 2 factorial is 2. And so f of 2 is equal to 0.084. That is a Poisson approximation to this binomial problem. Because those two things were valid, we were allowed to do that. Now, go back up with me to the binomial problem up here. If you actually did 100 combination with 2 times this, and do all the math here, this is actually going to come out to 0.081. So if we use the binomial function, which is the actual true answer to this kind of problem, we get 0.081. If we use the Poisson approximation for the same value, we get 0.084. So it's pretty darn close. Now it's only close because these two constraints are true. If the number of trials is like, let's say 10 trials, like some of the beginning examples we had back in the binomial thing, if we attempt to do this, the answer we're going to get down here is going to be significantly different, and so the approximation is going to break down. It's not going to help you. But if those two things are true, you're going to get a reasonable approximation out of it. Okay, now the next problem says you're playing roulette and you bet on number 7, the number 7 on the roulette wheel, for 200 spins. Okay, the probability of getting the 7 is 1 in 38 because there's 38 different places the ball can land on the roulette wheel. The question is, what is the probability of no wins in 200 spins? So what you want to really find out here is, you want to find out what is the probability if you spin that wheel 200 times that you'll actually will never win. What is that probability? You kind of get the idea and the basic feeling in your gut that it's got to be a low probability. Okay, the probability of winning is 1 in 38. If I spin that wheel 200 times and never win, that's a pretty unlucky day. So that's what we expect to get. We want to calculate that. And furthermore, we want to actually calculate it using a Poisson approximation if we can, just to get some practice with it. So first let's go into the problem and extract some information. We're betting on the roulette wheel. We know the probability of getting the success, so to speak, the landing on my ball and my number is 1 in 38. So we know what P is. That's the probability of success. We know that we're spinning the wheel 200 times, so that's my number of trials. And we know that we're trying to find out what the probability of getting 0 wins is. So X would be 0. The number of wins in 200 trials would be 0. So we know P, we know the number of trials, we know the number of wins in those trials. We have everything we need to write down a binomial distribution and calculate the answer. But let's go ahead and see if we can apply the Poisson approximation and get an answer that's pretty close. Okay? So in this problem, it's a binomial distribution with n is equal to 200 because that's the number of trials. X is the number of successes in those trials. I'm trying to find the probability of actually getting 0 wins. The probability of success is 1 in 38. That's given to us in the problem. And because of that, Q is 37 over 38. So Q is 1 minus P. And if you do 1 minus P, 1 minus 1 over 38 is 38 over 38 minus 1 over 38. 1 can be written as 38 over 38, so you have 37 over 38. That's the probability of actually not winning on that particular spin of the roulette wheel. Okay, so we know P, Q, X, and N. That's everything we really need for the binomial. But let's check, can we use the Poisson approximation? Two things have to be met. Is N greater than 100? Well, yes, it is, because N is 200. Is N times P less than 10? Well, let's check it out. N times P is 200 times P is 1 over 38. Okay, so 200 divided by 38, so what we get here is 5.26. That is definitely less than 10. So yes, both of these constraints are met, so we can use Poisson approximation to the binomial. Okay, with some measure of success, with some low error, okay? So let's go ahead and do that. What is the Poisson distribution function? First thing we need to calculate is the mean number that we're going to plug into that, which given, earlier on here when we talked about doing this approximation, you take that to be N times P, which we just calculated at 5.26, okay? Now, the actual function itself is mu to the x e to the negative mu over x factorial, but we know what mu is in our approximation. So it's actually going to be 5.26 to the power of x times e to the negative 5.26 divided by x factorial. Okay, so this is a function of x, just like anything else. This is a probability distribution function. We plug in different values of x. This is the number of spins, basically. And every number that we put in here is going to be the probability that that many spins will be 1 out of 200 spins. Okay, that's what we're doing here. But for this particular problem, we're wondering what is the probability of getting 0 wins out of 200 spins. So what we'll have is 5.26 to the power of 0 times e to the negative 5.26 divided by 0 factorial. Okay, so anything raised to the power of 0 is 1, and 0 factorial is also 1. So this is just e to the negative 5.26. So the probability of getting 0 wins out of 200 spins is 0.00518. Pretty low probability is exactly what we thought ahead of time, right? Because the probability of actually getting a success or winning the roulette is 1 in 38, okay? But if I spin 200 times and I never win, that's a pretty unlucky day, and this is a pretty unlucky day, so that's exactly right, okay? Now, if you use the binomial instead of this approximation to the binomial, which the binomial is going to actually yield the actual correct result, the probability of getting 0 spins is going to be equal to 200 in combination with 0 times p to the 0 times q to the 200. So p was the 1 in 38 and q was the 37 over 38. If we put all these numbers into a real binomial distribution for this problem, what we would get is 0.00438. Okay, if we actually calculate that. So you can see these two numbers are pretty close, okay? 0.518, 0.00438, they're fairly close. This is actually the correct answer using the binomial distribution. This is my 0 wins with my probability of winning. This is my 200 loses in a row with my losing probability, and these are the number of combinations of ways to do that, okay? That's the answer you get. So in this section, we've covered the probability distribution called the Poisson probability distribution, okay? And it's a distribution function that's pretty common. It's really used to calculate things like the number of events, the probability that a number of events will occur in a certain time interval, okay? Usually that's what it's for. Radiation decay, number of parts failure per year, things like that is really what it's really most useful for. But it can also be used as an approximation to the binomial distribution under certain conditions that we've outlined here. If those conditions are true, then you can calculate the mean value, which you have to calculate anyway to test to see if you can actually even use the thing, okay? And then once you've done that, you can plug it into the Poisson distribution, you'll get a number, and that number will agree with fair accuracy against the binomial distribution. You'll be giving up some accuracy in the answer. That's why it's called an approximation. So for some problems, they may ask you to do that, and that's really the short story on the Poisson distribution function.